Okay, so as per usual, I like to welcome all of our members and visitors. We are hosted both on the Zoom webinar with our membership. We're broadcasting through Facebook for those who are not members. So rather than take too much time trying to figure out who's a member and who's a visitor, let me just say welcome everybody. I'm going to turn this over to Jackie Weischer so she can announce our guest speaker.
Okay, are we ready to go? Yay, good deal. Okay, we got somebody kind of special, I think, tonight because he has the same name as our president, if you notice that, and he is also Rick's son. And Calen was able to come to Kansas City last year and speak at the Mid-States Regional Convention that we had in Kansas City, and it was quite good. So I figured maybe he would be interesting for you all to hear. He is a research scientist at IPAC at Caltech, where he splits his time working on the NASA Exoplanet Archive and using gravitational microlensing to detect and characterize exoplanets. Exoplanets are planets around other stars. Right, okay. So his presentation is going to be the road to 1 million exoplanets. And is that one behind you there, Calen? What is that?
Oh, this is actually Danielson Crater on Mars. This is a kind of an homage to the Perseverance lander.
Very nice. But anyway, I'm sure we're going to have a great talk, and I won't spend any more time explaining it. So thanks for being with us, Calen.
Well, thank you so much, and thank you for the introduction. Thank you for the opportunity to speak as well. As Jackie mentioned, right on about a year ago, came to Kansas City to give a talk at the MISRA, and of course, I would love to be there giving a talk in person right now. Unfortunately, that's not possible, but I appreciate everybody's work and effort to make this happen virtually. I know we're all still kind of learning how the ins and outs of telecom technology works. All right, so I'm gonna see if I can go ahead and share screen. We can get this party started. All right. Thank you again. I have ambitiously titled this talk, The Road to 1 Million Exoplanets. As Jackie mentioned, I'm a research scientist at Caltech. I did my PhD at Ohio State. I did a postdoc at the Jet Propulsion Laboratory, the NASA site that's just on the northwest side of Pasadena. And then about 3 years ago, just a little bit over, started working as a staff scientist at Caltech. My project work is on the NASA Exoplanet Archive, as Jackie mentioned, and I use primarily the lensing technique to detect and characterize exoplanets. Today, however, I'm going to give more of a broad overview, kind of a chronology of the history of exoplanet discovery, and hopefully I'll leave you with the impression that 1 million, if anything, is an understatement of where we're going to go in the next couple of decades as far as detecting, confirming, validating, and characterizing exoplanets. So I'm going to do something a little bit unusual. We're 2 slides in. I'm going to try an intermission. So the president, Rick Henderson, never say nepotism doesn't work. He and I did a test run to try to break up the monotony of a bunch of Zoom talking and talking heads. We're going to try twice throughout the talk, the first time now, to do something interactive. So Dad, if you could give it a shot, what we've got set up. Oh, great. Looks like it worked. So you should be seeing, for those of you who are on Zoom, a 3-question poll. So it's not a quiz. There's no identifying information attached, but there's 3 questions just to kind of get everybody's blood vessels flowing and get the brain circuitry going. So take a few seconds to look these over and pop in what you think your answers are. So for those of you who are on Facebook and who can't actually participate in this part, I'll read the questions. So question 1 is, Comet Neowise can currently be found near what constellation? And the options are Ursa Minor, Ursa Major, Hercules, and Cassiopeia. And then question 2 says, approximately how many confirmed exoplanets have been detected? And the options are 1,000, 2,000, 4,000, and 8,000. And then finally, my question number 3 is, what method was used to discover the first confirmed exoplanet? And the options are transit, radio velocity, microlensing, my favorite of course, direct imaging, pulsar timing, and orbital brightness modulations. So we'll take maybe another 30 seconds or so to let people kind of think these over and fill in their answers. As a speaker, I am not allowed to vote, but I will give the answers after we close the poll. All right, that's probably good. Dad, if you could, go ahead and close the poll, and there should be a button to show the results. There we go. Okay, it looks like we have a lot of responses. This is great. Thank you everybody for participating. So question 1, Comet Neowise can currently be found near what constellation? I know that I'm talking to a group of very, very keen observers, so I'm very happy to see the overwhelming majority of votes is for Ursa Major, which is correct, and I'll actually talk about that here coming up. Number 2, approximately how many confirmed exoplanets have been detected? Yet again, we have plurality correct. It is roughly 4,000. It's actually 4,197. You can say you heard it straight from an exoplanet archive scientist. And then number 3, what method was used to discover the first confirmed exoplanet? So the leading contender, the leading vote getter is transit with 41% of the votes. It is actually not transit. The second leading contender is orbital brightness modulations with 28% of the vote. It is not orbital brightness modulations. The third vote getter is radial velocity with 16% of the vote. It is not radial velocity. So then we have microlensing and pulsar timing are tied with 6% of the vote. It's actually pulsar timing. It's actually pulsar timing. And of course, in a talk titled The Road to 1 Million Exoplanets, we're going to spend some time on the very first exoplanet. So I'll give you a little bit of a history there. And for those of you who read the abstract earlier, there's an asterisk in me talking about the first confirmed exoplanets. And so let's just get straight to it. Thanks, everybody. We'll have another one of these toward the end of the talk. Kind of a quiz, a recap. All right, before I actually get going, there we go. Before diving into the exoplanet science portion of the talk, I figured, again, even though I know everybody here, or the vast majority of people are familiar with observing and have used POWL or the AIC or their backyard telescope, Comet Neowise is getting a lot of attention, and rightfully so. And so I figured I'd give a little tip, especially for those who are maybe not so proficient yet in observing, to figure out where to find Comet Neowise. So the white circles with the orange dot, it's showing every night, about 30 minutes after local sunset, where the comet can be found. And so you can see tonight, it's actually just south of the Big Dipper. And so as the nights increase, we're actually seeing it higher and higher in elevation, kind of really straddling or inhabiting that gap that's right between Leo and the Big Dipper. I'll note as well that tonight should be particularly good because we're just a couple nights after the closest approach. So that was about 8:10 p.m. Central Time, the night of July 22nd, and Comet Neowise was about 64 million miles away. And something I didn't know until just earlier today is that this comet last came into the inner solar system 4,000 years ago. And it won't be back until another 6,500 years from now. So it really is a once in a lifetime opportunity, and that's if you're lucky. So I'll share a couple of images that friends and colleagues of mine have taken. So this was taken by a friend of mine, BJ Fulton. He's another research scientist out at Caltech with me. This is in the San Gabriel Mountains, which is just north of Pasadena in California, or Nasadena, as I refer to it. And you can see Comet Neowise right there. This is actually about 10 days ago. And this is taken with his digital camera, but this is a very short exposure. And he said this was pretty close to what he could see with dark adjusted night vision using his naked eye. This is an image he took from the same spot in the Angeles National Forest. It's a place overlooking the Big Tuhunga Reservoir, for those of you who are familiar with the area. And this is a stack of 30 2-second exposures using Nikon D5500. Here, it's really, really booming. So this underscores that while you can see it, if you're in a good spot with your naked eye, if you have binoculars or a good camera, or especially if you have a telescope, it really should be prime viewing. And in fact, there should be no excuses. Here's an image that's taken a 5-second integration time. This is on the eastern edge of the Santa Monica Mountains. So this is just west of the Hollywood sign in LA. This is taken by another friend and colleague, David Kirkpatrick at IPAC. And here you can see Comet Neowise. It's just above a peak called Cahuenga Peak. And so if we can see it over the LA skyline, I think y'all should be hopefully more than able to see it pending clouds and whatnot. All right, let's jump in. The road to 1 million exoplanets begins with our first 3 exoplanets, and the story starts about 2,300 light years away at a pulsar. So here I'm showing an animation of exactly what a pulsar is. So this is a highly magnetized rotating neutron star. So there are beams of radio wavelength electromagnetic radiation that are being emitted from the magnetic poles of this neutron star. So this is the end of life state of a star that begins its life with about 10 to 25 times the mass of the sun. And what happens is you see this kind of lighthouse effect. If the inclination angle between us on the Earth, where our telescopes and our eyeballs are, and a given neutron star works out, you'll actually see this periodic increase in brightness from the neutron star as the beamed emission rotates into and out of our line of sight. So this example neutron star, it has an orbital period of a little bit more than 1 second. And it turns out that regardless of the period of a neutron star, the timing of these pulses, it can be measured extremely precisely with uncertainties even in parts per million. And so what happened is Alex Wolshin, who's an astronomer at Penn State, he was studying a pulsar named PSR B1257 plus 12. Back then, there weren't really conventions for naming exoplanets because people hadn't discovered any. And he was observing it, I think in 1991 and 1992. And he noticed delays in the arrival times of this beamed emission from the rotating neutron star, from this pulsar. And one of the ways that you can get deviations from a purely periodic signal is if you have massive bodies orbiting the pulsar. And so indeed, it turns out that he discovered there were 3 massive bodies, all of which have mass roughly the mass of the Earth. I say roughly to indicate that they're terrestrial mass planets, not Jupiter or ice giants or gas giants. So this is an artist rendition of this pulsar with its 3 exoplanets. They range in mass specifically from about 0.02 times the mass of the Earth. I'll note that that is only twice the mass of the Earth's moon. And then the outer 2 planets, planets C and D, have masses about 4.3 and 3.9 times the mass of the Earth. So this was a shock. This was, you completely blew the lid off of what people thought was possible. Because not only had no one detected any planets outside of our solar system yet, but the last place that anyone would have thought to look was around a highly magnetized rotating neutron star, some sort of stellar remnant. I'll note as well that this star, PSR B1257 plus 12, its orbital period is actually 0.006 seconds. So it belongs to a class of objects known as MSPs, or millisecond pulsars. So if we were observing that, able to observe that with our naked eye, those beams that we would see from the previous animation would be occurring about 200 times as frequently. Planet B, the low mass planet, remains the lowest mass planet that has ever been discovered outside of our solar system. It still holds the record even now. So if we fast forward to the kind of conventionally told story, these were all of the known planets in 1994. So we're zooming ahead 2 years. And I say all with several asterisks. So the history books often forget to mention the pulsar planets, even though those were discovered 2 years before our current story. And of course, back then in the mid-90s, Pluto was still a planet. And so it's not included on this diagram. But actually, in the 90s, there were 9 known planets. Then, the end of 1995, 23rd of November, everything changed. And this is what really, really opened people's eyes to not just that we could detect planets, but that they might actually be quite common. So I put up the paper title. So they called it a Jupiter mass companion to a solar type star. Even a few years after the discovery of the pulsar planets, there was a lot of skepticism, given that a stellar graveyard is not the first place you would expect to find Earth mass planets, let alone 3 of them. However, this signal seemed pretty incontrovertible. So I'm showing on the y-axis, this is the radial velocity amplitude. This is showing how the tug of the planet on the host star affects its relative motion as a function of orbital phase. So it's what we call folding on the period. It's not strictly a function of time, but you can think of it as a function of time. And the signal is a clear sinusoidal signal. And from this radial velocity measurement, from the radial velocity technique, you can actually set a lower limit on the mass of the object, as well as determine its eccentricity, its orbital period, and a couple of other factors. So here is what the picture, again, setting aside the pulsar planets, even though those technically got the flagpole in first. And what was found orbiting 51 Peg, the star whose light curve I was showing earlier, was pretty astonishing in a lot of ways. Not quite Earth mass planets around a rotating neutron star, but still just as shocking, something for which we don't have an analog in the solar system. So imagine taking something that's the mass and radius of Jupiter and moving it closer to its host stars such that its orbit is interior to the orbit of Mercury. And that's exactly what we have. So 51 Peg B is the name of this exoplanet, and it had an orbital period of 4 days and a planet mass about half the size of Jupiter. And so this led to a classification of planets called hot Jupiters, in particular because we just didn't have anything such as this type of object in the architecture of our own stellar system. So as I mentioned earlier, this was discovered using the radial velocity technique. And so as I discuss the techniques, I'll give a little bit of an overview of how they work. So the RV technique refers to the measurement of the reflex motion of an object, of a star, as a massive object orbits it. And so you can see in the kind of toy model Doppler shift below that as the planet and the star actually orbit their common barycenter, their common center of mass, the light that we would measure from the star is red shifted and blue shifted as the star is moving away from us and toward us. And I think of this method as what I call an indirect method. So you're looking at the light from the star. You're not actually directly detecting the exoplanet, but you're able to infer the presence of a planet due to the observed properties of this host star. So much to Alex Wolshin, the pulsar planet discoverer's chagrin, late last year, the Nobel Prize in Physics was announced, and for the first time, exoplanet science was recognized. Not only was it recognized, but it got half the prize. So as the Nobel Committee's rules go, a Nobel Prize cannot be shared by more than 3 people. And so one of the people who got half, and he got half the prize, is Jim Peebles for his extraordinary contributions in cosmology. And the other 2 people who collectively split the other half of the prize are Michel Mayor and Didier Queloz. So they each got a quarter of the prize. And specifically, it wasn't for the discovery of the first exoplanet, and the Nobel Committee knows this. but they got the Nobel Prize for the discovery of an exoplanet orbiting a solar-type star. So 51 Peg, the star that hot Jupiter is orbiting, has roughly the mass of our sun, and it's a mid-G dwarf. So all of us who are following the footsteps of Michel Mayor and Didier Queloz recognize very much that we're standing on the shoulders of giants, as the saying goes. One instance in which I got to actually indirectly meet Michel Mayor was at a conference in late 2016. So this is before he was a Nobel laureate. We were both at an exoplanet conference in 2016, and we each volunteered to go up on stage and learn how to hula dance. So this video, which has not been doctored, is showing yours truly, kind of tan shirt, orange shorts on the right, and there you can see the characteristic beard of now Nobel laureate Michel Mayor. And here we are, trying to learn desperately how to hula dance during an exoplanet conference in Hawaii. Now, usually when I tell people that I was fortunate enough to share a stage with a Nobel laureate, they get very excited, and I have to quickly explain that it's not really what they think. It's not really in the way that they're imagining. So fast forward over 15 years, and we get to the Kepler mission. So in the late 90s and early 2000s, we saw many more, hundreds more exoplanets get discovered through using the radio velocity technique. And then a technique called the transit technique came along as well. HD 209458b, another kind of mouthful phone number, was the first planet to be discovered using the transit technique. And it was also measured, its Doppler signal was also measured. So it was detected in both RV and transit, but it was first discovered in transits. And eventually, starting in the late 90s, a mission concept that was unnamed at the time, but wanted to use the transit technique to actually survey a large number of stars and see how many planets it could detect. And eventually, the goals of this mission evolved and morphed into the space telescope that we know and love called Kepler. And so Kepler, which launched in March 2009 into an Earth-trailing solar orbit, it's about a quarter phase behind the Earth going around the sun, stared at a patch of sky for roughly 3.5 years. Its nominal main mission lifetime, I think, was 4 to 5 years. Unfortunately, a couple of the gyro wheels failed, and so it was not able to go to full term. But it still gave us a bunch of exciting results I'm going to talk about. And it observed this patch of sky that's here in the constellation Cygnus the Swan. So its full field of view is 105 square degrees. And you can see those white rectangles outlining its survey area. Vega is just off to the side on one edge, and Deneb is down there. And you can see it's just above the galactic plane. And so Kepler used the transit technique. And the transit technique is another indirect exoplanet detection technique. So here again, we're inferring the presence of a planet by observing its effects on its host star. So what we're watching here is as the orbit of a planet takes it in front of its host star, it actually blocks the light. Not that planets are completely dark, they're just so much fainter than their host stars that for all intents and purposes, they're generally opaque as they cross the disk of the star. And so we can take this dip in flux, this decrease in brightness, as a measurement of roughly the radius of the planet. Technically, it's the ratio of the square of the radii of the planet over the host star, because we're looking at the area, the circle of the planet, over the area, the circle of the star. One of the most salient features, though, as we see here, is that you have a larger planet. Since it has a larger radius, and thus a larger area, that decrease in light is going to be larger. So larger planets, which are generally more massive planets, give you bigger dips and are thus easier to detect. Smaller planets are smaller dips and harder to detect. Now, before I go into the results, I'm going to remind everybody of our spectral classification system. So we've got stellar luminosity on the y-axis, and we've got temperature on the x-axis. So if you're in the very bottom right, you're very dim, you're not very bright, you're not very luminous, and you're cool, which means lower temperature, redder star. And the color-coded bar at the bottom tells us the spectral classification system. So we have O stars, which are very hot and very luminous, and which are generally a few tens times the mass of the sun. O, B, A, F, G, K, M, and we get all the way down to lower mass stars, which get down to roughly 0.1 times the mass of the sun and are much cooler. So what are the main results from Kepler? Here I'm showing a recent result that's done a complete post hoc analysis of the complete survey data set from Kepler. And there's a lot of numbers, a lot of boxes, but the real takeaway is the color coding here. So on the y-axis is the radius of a planet in Earth radii. So it's an Earth radii. It's half an Earth radius at the very bottom. And at the top, it's 16 Earth radii, which is more than the radius of Jupiter. And on the bottom, we're looking at the orbital period. So it's about 0.78 days. So that's even shorter than 51 Peg-B, out to about 400 days. So that's just a little bit longer than the Earth's orbital period. And what we're seeing here is in different bins, in different groups of planet radius and orbital period, we're looking at the measurement of the fraction of stars, FGK stars. So these are stars with spectral types very similar to our sun. The fraction of these stars that host planets. And green, as you go from red to green, you go from not very many to more stars that host planets. So red bottoms out at less than 0.1%, 0.01%. But green colors indicate that there are roughly more than 1% of those stars host planets. We can look at this in a little bit more of a user-friendly way here. So this is a graphic put together by the NASA Kepler mission that shows the average number of planets per star. And instead of a two-dimensional grid that we were looking at before, here we're just looking at it as a function of one parameter, the planet size. So this is the same as the radius. So 1 here means radius equal to the Earth. And so we can see that planets are extremely common. The average number of planets per star, just for that lowest bin with planets with 1 to 1.4 times the radius of the Earth, is over 30%. And it stays constant at about 25 to 30% until you get to planets with a radius about 3 times that of Earth. So if you were to integrate or sum across this whole plot, you would see that on average, there's slightly more than 1 planet per star. So one of the big takeaways that Kepler showed us is that planets are extraordinarily common. So maybe it wasn't so weird that Alex Wolshin found Earth-mass planets orbiting a rotating neutron star. And maybe it wasn't so expected that the radial velocity was able to find a very massive planet even as far back as the mid-90s. And I'm showing at the top here, these are our solar system planets to kind of guide what types of planets we're considering here. So we can see the very right edge of this plot is getting into the gas giants. The middle is the ice giants, or analogs to Uranus and Neptune. And the left side are terrestrial analogs, so rocky planets such as the Earth and Mars. So Kepler also showed us that Earth-sized planets are common, and I don't even need to show a different graph. Here we can look at these lowest radius bins, 1 to 3 times the radius of Earth, and we see that that dominates the detections that Kepler has found. So not only are planets common, but Earth-sized planets are very common. In the range 1 to 3 Earth radii, there's roughly 1 of those per star in our galaxy. This is not something we expected. This is not something we would have known before launching Kepler. So another thing that we learned from Kepler is that multi-planet systems are common. So I know everybody's in their respective homes. So feel free to light up whatever your drugs of choice are and watch as this zooms in. So this is an animation that's showing all of the multi-planet systems discovered by Kepler. So this is, we're referring to it as an orrery. The size of the planets is scaled according to the relative radii. They are color-coded according to the equilibrium temperature of the planets, where redder is hotter and bluer is cooler. A deep blue is roughly the temperature of the Earth. And the distances from the solar system are correct, but the spatial distribution is not correct. These come from Kepler, so if they were actually put in the correct place in the sky, they would all be in one cone, given that Kepler just looked at one patch of the sky. So just to give some statistics, there are, at the time that this was made, the number has increased since, there are 659 multi-planet systems, 280 systems that have 2 planets. We know of a few systems that have large numbers of planets. So our solar system, again, after the demotion of Pluto, has 8 planets. The Kepler 90 system has 8 planets. And there are 3 different systems that have 7 planets. The closest multi-system is about 15 light years away. This is Gliese 876. It has 4 systems. And there are actually 12 systems within 50 parsecs, which is about 150 light years, that have multiple planets orbiting them. And one of those 7 planet systems we're gonna come back to a little bit later. And those of you who have followed exoplanet science closely probably already know which system it is that we're going to talk about. So to sum up, the Kepler mission looked at about 100 square degrees. It observed over 500,000 stars. And to date, it has discovered 2,662 confirmed exoplanets. And that diagram on the right is showing all of those dots, one for each exoplanet that Kepler has discovered. An attribute of Kepler that doesn't get quite as much attention, but is that there are a little bit over 2,400 planet candidates that are still awaiting validation and confirmation that were detected by Kepler. So roughly equal numbers so far of confirmed exoplanets and candidate exoplanets awaiting confirmation. So we went from 0 exoplanets in 1991 to 3 in 1992, to our first RV planet in 1995, to in the post-Kepler era. So this gets us to 2013, 2014, 2015, roughly those years. Now we're talking thousands of exoplanets. And this led to a colleague of mine, Eric Mamajek at JPL, to make this diagram. And so what we're showing is on the y-axis, this is the cumulative number of exoplanets. How many planets do we know about that have been confirmed outside of our solar system? And it's in log units, so log base 10. You can see it goes 1, 10, 100, 1,000. And we're looking at this as a function of time. So each black dot is the total number of confirmed exoplanets in that year. And you can see 1989, 1990, 1991, it's hovering down there. It's actually at 1. And that's because there was at the time, there was an object that was thought to be a planet that was later discredited. And so then it jumps up, we can see the pulsar planets, and then 51 Peg-B, again, which led to a Nobel Prize win. And then there's HD 209458b, that's the first transit planet. Ogle is one of the ongoing ground-based microlensing surveys. So that's the first microlensing detected planet in 2003. HR 8799, those are the first direct imaging planets. And then we get into the Kepler era where the lid really is blown off. And he said, you know what? This looks kind of like a straight line in log space. So I think I can fit that with a power law. And what he found is that not only is this distribution well fit with a power law, but that the doubling time, or the amount of time it takes or has taken over the past 25 or so years for us to double the number of known exoplanets, is about 27 months. So every 2 years and 3 months, the number of confirmed exoplanets has increased roughly by a factor of 2. And this is what the inspiration for this talk really is. If that continues, that doubling, we're really not that far away from reaching 1 million or even 1 billion exoplanets, over the next several decades. So I want you to keep that in the back of your mind. We're going to really circle back to the rate of exoplanet discovery, but I want to focus on a system that I think really underscores 2 of the things that we learned from the Kepler mission. So this is an actual image of the actual front page of the New York Times on Thursday, February 23rd, 2017. So this is a little bit after Eric Mamajek made that plot that we were just looking at. And lo and behold, we have the TRAPPIST-1 system. So this is a system with seven exoplanets, all of which are roughly the size of Earth, all of which are terrestrial, meaning rocky, so high density, and all of which are orbiting pretty close to their host star. So I'm going to show an animation. Here, each of these colored lines indicates the orbit of one of these TRAPPIST planets as they orbit the host star, which is known as TRAPPIST-1. TRAPPIST-1 is an ultra-cool dwarf. So if we again go back to our Hertzsprung-Russell diagram and remind ourselves of the spectral types, that means that it's a very cool or low temperature and very low mass star. So it has a mass of about 0.1 times the mass of the sun. What we're looking at here are the actual data as TRAPPIST-1 was observed by the Spitzer Space Telescope. And you can see the photometric measurements, the measurements of the light from the host star, as Spitzer observed it continually for 21 days, and color-coded with the planet dots and the planet orbits are the actual transits for each of these planets, B, C, D, E, F, G, H, all the way to 7 planets. And you can see, even though each of the planets has a regular period, the spacing of the periods due to this high number of transiting planets leads to some wild features in the light curve, where you actually get coincident transits, sometimes of even more than 2 planets. It's really quite an impressive system. So how does TRAPPIST-1 stack up to the solar system? So I'm showing at the top the relative orbits of the Galilean moons around Jupiter, and scaled to the same orbital separation. The middle section is showing TRAPPIST-1. So there's the 7 different planets, B through H. Their masses again range from 0.3 to about 1.2 times the mass of the sun. Their periods are from 1.5 to 18.6 days. So you can see B and C roughly have the same distance from TRAPPIST-1 as Callisto does from Jupiter. And there you can see again that our sun is several times larger than TRAPPIST-1, about 8 to be exact. If we then instead compare it to the inner solar system rather than Jupiter, we can see that all of these planets are well interior to the orbit of Mercury. So it's a very compact system and would easily fit inside the orbit of the innermost planet in our own solar system. One of the many amazing features of this system is that the eccentricity of each of these planets is less than or equal to 0.01, so very circular orbits. And their inclinations are all between 89.5 and 90 degrees. And so that's what allowed us to get really, really lucky and observe transits of all of these planets. So now what I would have done is color-coded the orbital separation according to roughly what the habitable zone is. So red is where water at standard temperature and pressure would boil, blue is where it would freeze, but green is roughly where it would exist as a liquid. So we see not only are there densities measured for several of the planets, but for one of those, E, which we from the density know is rocky, E is actually on the inner edge of the habitable zone in TRAPPIST-1. So not only is it a treasure trove as far as studying orbital dynamics and long-term stability and looking at coplanar orbits and using the transit method, especially to study stars that orbit study planets that orbit a host star that is spectral classification very different from our sun. But we actually have a low mass terrestrial planet in the habitable zone, which is very exciting. This has led to a lot of very cool graphic design projects, both in and outside of NASA. So here's one cool way to visualize the snow line. So you can see the planets in the TRAPPIST system that are very close to the TRAPPIST-1 star are steaming. Those that are kind of at an intermediate distance, you can see there's liquid water droplets, and those that are out past the snow line, there's actually solid water crystals there. The Exoplanet Travel Bureau one of the organizations at JPL that focuses on the intersection of art and science, created one of their posters to focus on the TRAPPIST-1 system. All right, I'm gonna skip this animation actually in the interest of time. I'm gonna go to the next slide. We've talked about Kepler, and we talked about how Spitzer was used to discover 5 of the TRAPPIST planets and confirm the other 2. And the current major mission that's ongoing to discover exoplanets is called TESS, the Transiting Exoplanet Survey Satellite. So this is using the transit technique, and it's observing what are called sectors. So it's got 4 wide field cameras, 26 degrees on a side. So one of these cameras is observing on an area much larger than that of Kepler. And one sector is comprised of a pointing for 4 of these cameras stacked on top of each other, as you can see on the left. And it observes a sector for 27 days, and then it rotates to the next sector and observes that sector for 27 days. And then it rotates and looks at the next sector. All said and told, it goes through 13 observation sectors per hemisphere of the celestial sphere in roughly 1 year's time. Then it flips to the other hemisphere, flips across the ecliptic, and does 13 sectors there in roughly another year. So the diagram on the right is showing for the entire sky, because this is observing nearly the entire sky, 4 pi steradians of solid angle, which areas of the sky are being observed for how long. So even though one sector is only observed for 27 days, you can see that there's overlap between a lot of the sectors, to the point that during a 1-year observing campaign, near each ecliptic pole, there's actually regions that are being observed nearly continuously. And this overlaps with the region that JWST would be able to view continuously through no accident. So TESS has discovered 66 confirmed exoplanets so far, but it recently got extended so that its mission is going on another 2 years. That means it's going to be able to do each ecliptic hemisphere again. And it's in a very, very stable orbit. And it is likely that the TESS mission will get extended, honestly, several times. The stable orbit means that its main expendable fuel is not really a bottleneck. And it's doing incredible science, and it does not cost very much to operate. So I think that NASA will extend this several times over. So what we're looking at is a chart that's predicting, this came out a couple years ago, how many planets TESS will discover by the end of just a 4-year mission lifetime. So the x-axis, again, is showing this is a function of planet radius. So lower radius, smaller planets to the left, larger planets to the right. So Earth is the leftmost box, and Jupiter and planets larger than Jupiter is the rightmost box. And then in between, we have ice giants. And gray is referring to one observational mode that TESS has, in which it downloads full frame images every 30 minutes. And then it takes higher cadence 2-minute snapshots of individual stars that were on a pre-selected list. So we see that for Earth-sized planets, in total, including these FFIs, the full frame images, and the higher cadence 2-minute exposures, TESS will discover roughly 41. If we go to higher radius planets, larger planets, TESS will discover 12,000. So this whole plot predicts that TESS will discover a little bit more than 14,000 planets. And of course, that's for a shorter nominal mission lifetime. The longer and longer TESS goes, the more and more planets it will be able to discover. So before we conclude with one final space mission, I want to give a shout out to the direct imaging technique. So this is, as you might expect, the method for directly detecting exoplanets. So here we're looking at the HR 8799 systems. This is the first, the system with the first exoplanets discovered via direct imaging. And you can see the 4 blobs that are orbiting around the host star, HR 8799. And these planets, we're actually seeing the light from the planets, not just reflected emission. This is actual thermal emission from these planets. And they're very massive. So these are all super Jupiter planets, roughly several times the mass of Jupiter. And the orbital periods span from decades to centuries. So these are extremely far out planets. And part of the reason that we're able to directly image them is because they're orbiting a young host star, because they are so massive, and because they are so far away. So you block the light from the star, and then you're actually able to see this thermal emission from these young planets before they've fully contracted. The main reason I want to highlight direct imaging is a result that came out earlier this week. And this is something that my office mate and good friend, a scientist named Tiffany Meshkat, was involved in. So this is an image taken using a telescope called VLT down in Chile. So this is actual data. And these are two, again, super to Jupiter mass planets orbiting the star TYC 8998-760-1. This is a star that's about 300 light years away and has a mass almost exactly equal to that of our sun. And this is the first ever image of a multi-planet system around a sun-like star. So whereas direct imaging is not going to boost greatly, at least, the number of planets as we're on our road to 1 million, it is able to provide characterization and direct detection of exoplanets in ways that the other techniques can't. So last but not least, I'm going to tell you a little bit about the gravitational microlensing technique. So again, this is what I use to detect and characterize exoplanets. So I refer to microlensing as a doubly indirect planet detection and characterization technique. So what we're seeing here in the top panel is the light from a source star, a background object. That's the bright circle that goes across horizontally. And we're watching as the light from that star is split into two images. And so those are the yellow ovals that trace out those shaded regions. And that light is being split because of the lensing due to a massive foreground object, such as a star. And if that star happens to be orbited by a planet, what you see is a light curve that's similar to what we see at the bottom. So not only is the light from this background source star lensed and separated, but it's actually magnified. And so in the bottom panel, you can see we see the light from that host star get brighter as the lensing event occurs. And if there is a planet overlapping the trajectory of one of those images, which you can see kind of at roughly 2 o'clock in the diagram on the top, that planet will also perturb the light of the image of the host star, of the source star. And so that's how you get this extra perturbation and this magnification structure in the light curve. So there's an upcoming space telescope that will launch after JWST. So we're talking 2026, likely at the earliest. And it's been referred to as WFIRST for the Wide Field Infrared Survey Telescope. I need to update this slide because just recently the telescope was renamed after Nancy Grace Roman, who is one of NASA's chief scientists. And she was instrumental in creating the Hubble Space Telescope. So I'm going to refer to WFIRST as the Roman telescope, which is its new name, but you might see WFIRST on some of these slides. And and there I do it again. And Roman is going to conduct a large-scale survey of the very galactic center and use the microlensing technique to detect exoplanets. And so here I'm showing the field of view of the actual camera array for the Roman Space Telescope. And I'm showing it in comparison to the Webb Space Telescope in yellow and Hubble in red. And it turns out that Roman will have a field of view that's about 100 times that of both JWST and Hubble. So an extremely large area coverage. So to bring this all the way back to Kepler, here we have a diagram that's showing kind of a top-down view of our solar system. And those are the planets labeled, and dwarf planets in the case of Pluto. So that's Jupiter, Saturn, Uranus, Neptune, and then Pluto. The red colored area is what Kepler's search area was. So Kepler, using the transit method, was able to probe close-in planets to its host star. roughly a few 100-day orbits and closer. So that's around the Earth's orbital period and shorter. And we can zoom in and see that this is really, really excellent for covering the types of orbital periods that we know the rocky terrestrial planets in our own solar system have, such as Mercury, Venus, Earth, and Mars. What the Roman Space Telescope will do with microlensing is probe farther reaches within stellar system architectures. So microlensing is not a technique that is super strongly suited toward detecting planets that are very close into its host star, to their host star, but it is very well suited for detecting planets that are a factor of several times farther away. Not quite as far away as direct imaging is sensitive to, but in between transit and direct imaging. And so it's not really fair to show this in linear space, but it appears, that the Roman Space Telescope using lensing is going to access a much wider area than Kepler. But the most fair thing to do is to actually look at this in log space, because that's how we think planet formation occurs. It's not a linear process. And so what I'm showing is the planet mass in Earth masses on the y-axis, 0.01, which is about the mass of our moon, up to 10,000, which is more than 10 times the mass of Jupiter. And on the x-axis is the semi-major axis in AU. So here, the Earth's orbital separation is 1. And I've overplotted the solar system planets to give a guidance of where they would be in this two-dimensional diagram. So there's 3 different colors of points here. So black points represent radial velocity detected planets. Red points, and the red kind of trapezoidal curve identifies those planets detected by Kepler using the transit technique. And the red solid line roughly demarcates the survey sensitivity limit of Kepler. And so you can see that Kepler didn't quite get to what its main goal actually was, which was measuring the fraction of solar-like stars that have Earth-like planets. Earth is just outside of that survey sensitivity region for Kepler. The blue points and the blue curve show the results of a simulation for what the Roman Space Telescope will be able to access using microlensing. And so here, while Earth lies just inside that blue sensitivity curve, it's actually not going to detect very many Earth mass planets with an orbital period of 365 days at 1 astronomical unit. However, the complementary nature of Kepler and the Roman Space Telescope means that we'll be able to interpolate between these 2 populations of detected planets after the Roman survey is complete and measure eta Earth, which is this fraction of Earth-like planets in the habitable zone around sun-like stars. One thing I'll point out on this diagram is that W first, now Roman, will be able to detect planets with a mass down to the mass of the moon Ganymede. And Titan, optimistically, is maybe just barely within reach. So to really round out our path to 1 million exoplanets, what I'm showing here is similar to a plot I showed earlier for Kepler. So this is the result of a simulation predicting the number of planets that the Roman Space Telescope will detect, specifically using microlensing and transit combined. Since the microlensing survey is just a time series survey, you can look for lensing signals and you can look for transit signals. It's not going to be able to characterize those transiting planets as well as it will be able to characterize the microlensing planets, but it'll still detect them. So on the top, you see different bins of planet radius. So the first 3 show 2 to 4 Earth radius planets, 4 to 8 Earth radius planets, and greater than 8 Earth radius planets. So you can think of that, roughly speaking, as terrestrial planets, and then ice giants, and then gas giants. And so the 4th column is showing you the total number of planets that will be detected. And the right column is showing you how many stars will be observed. And we're seeing this as a function of different spectral types. So again, we'll harken back to our Hertzsprung-Russell diagram. The top row is for F dwarfs, then G dwarfs, such as our sun, then K dwarfs, and then M dwarfs. And so you can see, if we look at the orange column with total planets, there's well over 100,000 planets that will be detected between transit and microlensing. Again, the vast majority of those will be transit, but the ones that will be characterized will be microlensing. So to conclude, I'll leave everybody with this slide. So this is a graphic put together by NASA that shows a lot of the missions that we've been talking about today. So these are any space and even ground-based missions, whether launched and operated by NASA or European or joint NASA ESA missions. And we've talked about Spitzer, which was crucial for discovering 5 of the TRAPPIST planets and confirming the other 2. Kepler, which conducted the first large-scale space-based exoplanet survey. TESS, which is operating right now. JWST, which it was just recently announced, will be delayed yet again, but currently has a nominal launch date of Halloween next year. And then leading into the Roman Space Telescope. And so between all of these missions, we've gone in the past 30 years from no known exoplanets to thinking that pulsar planets were crazy to over 4,000 confirmed exoplanets right now, 4197 as of today, to with TESS and Roman on the horizon, not to mention Gaia, which will detect planets via astrometry, but which I didn't really discuss today. The net yield of these will leave us in the several hundreds of thousands, marching on toward 1 million exoplanets, hopefully in the next few decades. So to conclude, if I could have Dad put up the second poll. Now we're going to do kind of a recap to see how many people are paying attention and to see what everybody learned. So if you could show the second poll. Great. Here we have. So again, no names are being recorded, so don't worry if you don't get the answers. But the first question for those of you on Facebook is, which space telescope has discovered the most exoplanets, confirmed and candidate? And the options are the Hubble Space Telescope, the Spitzer Space Telescope, Kepler, and TESS, the Transiting Exoplanet Survey Satellite. So question 2 is, what method will the Roman Galactic Exoplanet Survey employ? So option 1 is the transit method. Option 2 is the radial velocity method. Option 3 is microlensing. And option 4 is direct imaging. And then finally, question 3 is, statistically, how many exoplanets are there per star roughly? And the options are 0.1, 0.5, 1.0, or 10. So we're looking at which space telescope has discovered the most exoplanets, what method will the Roman Galactic Exoplanet Survey employ, and then roughly how many exoplanets are there per star. So let's go ahead and close the poll and see how everybody did. Oh, great. Everyone really looks as though people are paying attention. Fantastic. Or you're already very smart and knew the answers even before I said them. So number 1, which space telescope has discovered the most exoplanets? Far and away, Kepler, 96% of the vote, 100% correct. Well done. So number 2, what method will the Roman Galactic Exoplanet Survey employ? So this one was a trick question, and it was actually a trick question for 2 different reasons. So 72% of people said microlensing, and that is the main method that the Roman survey will use. And that's what's driving the actual observing strategy. But as I mentioned, it will also use the transit method. So though the 12% of you who said transit, you are not incorrect. That is good. And actually, even though I didn't mention this at all, the Roman Space Telescope will have a coronagraph. So that's an instrument used to conduct direct imaging. And so 8% of you said direct imaging. It's not going to be the main focus of the survey. It's a totally different observing mode. But the Roman telescope will conduct a technology demonstration of a space-based CGI or coronagraph. And then finally, how many exoplanets are there per star, statistically speaking? A little bit over 1. And 56% of people said 1. So on average, there are slightly more planets in our galaxy, statistically speaking, than there are stars. So thank you. I realize that was a little bit on the long side, But thank you for your patience. Thank you for having me to talk, and I'm happy to take any questions now.
Calen, if you have your question and answer window open, there's 3 questions on there that you might want to take a look at. Now I can read it to you.
All right, Q&A. I hope I'm pronouncing this right. Gerald Williams asks, what percentage of stars do you believe have planets? 25%, 50%, 75%, and 100%. I love the way that this question is phrased because I don't have to say how many I think. I get to answer how many I believe. I believe somewhere around 100%, 75 to 100%. The fact that we found planets orbiting nearly every spectral type that we can think of, not quite yet around O and B stars, but around A stars. The fact that we've found them around evolved stars, so not just neutron stars, but white dwarfs, as well as a class that are colloquially referred to as retired A stars, or A stars that are subgiants on the subgiant branch. And the fact that we have seen just how common planets are, I believe that it's no accident that we found so many and that an extremely high fraction of stars has planets. One thing to keep in mind is just because we don't detect a planet around a given star in the night sky does not mean it does not host any planets. All of these techniques that we've discussed, transit, radio velocity, direct imaging, microlensing, pulsar timing, they have different biases and selection effects. Perhaps I think the easiest to understand is transit and radio velocity. There you have to have a nearly edge-on orbit, close to an inclination of 90 degrees, or you're not going to be able to detect a planet. So 90 degrees or 85 to 90 degrees is not very much phase space. So you can have planets that are face on or that are close to edge on, but just not exactly edge on. That just might not be detected at all. If the planet doesn't pass in front of the disk of the star, you'll never see a transit signal. And so when we fold in these kinds of selection effects, our actual understanding of the fraction of stars that have planets is driven by folding these biases into our rates and understanding that if we look at 10 stars, one of them has a transiting planet, well, we would expect that we wouldn't actually see a signal from most of those stars. And so we can statistically extrapolate. How many do I think have planets? Also close to 100%. All right, second question is from David Johnson. You get a light phase shift if side on to orbits. What do you see if sitting top down on orbit? So this is a great question. And this folds into the previous question as well. So if you're using the transit or radio velocity technique and you're looking top down, you won't see a signal at all. If that's what we refer to as an inclination of 0. So you would see it kind of as you would a clock face where it's perfect circles. However, if you were to tilt that 90 degrees, that's what you're referring to as edge on. Or side on. That's when you would see signals. However, other techniques are able to detect planets that have orbits that don't necessarily need to have inclinations of 90 degrees. So microlensing and direct imaging are great examples of detection and characterization techniques that are, I'll use the phrase agnostic to inclination. Microlensing does not allow you to measure the inclination, and it actually doesn't care. It cares more about the projected separation. How far away in the plane of the sky is the planet at the time of the microlensing event? So yeah, it really depends on the technique is the answer. Transit and RV, you wouldn't see a signal. Microlensing and direct imaging, you still might. I'm gonna skip Gerald's second question just to get through everybody else's questions. Bill Barlow asks, what is the most distant exoplanet found so far? So it's actually one detected by microlensing. I didn't really get a chance to go into this. But one of the big benefits of microlensing is that it's able to detect planets at a wide range of heliocentric distances. So the most distant exoplanet is actually on the far side of the galactic center. So we're about 25,000 light years away from the center of our Milky Way galaxy. And there have been a handful of planets, all discovered by microlensing, that are on the opposite side of the galactic center. And there's one that has been discovered that's about, we think, 13,000 parsecs, which is nearly 40,000 light years away. Very, very impressive stuff. Now, the kinds of characterization that you would get with direct imaging and transit, looking at the atmosphere, measuring the density, we can't do that at all through any stretch with microlensing, but we are able to probe planets in a wide variety of environments, including the galactic bulge and most distant. I'm going to use this question as a jumping off point to say as well that I certainly think that within the next 25 years, we'll see our first planets discovered, not just outside our solar system, but outside our Milky Way galaxy. And based on the techniques we have available, it will almost certainly be either transit or microlensing. So you can say you heard it here first. All right, Jim Stevens asks, any comment on the Fermi paradox, given what we know now about the number of planets? So for those of you perhaps unfamiliar with the Fermi paradox basically starts with the Drake equation and tries to estimate how many intelligent civilizations there might be. And the first couple of inputs, the first couple of terms in that mathematical equation are how many stars are there in our galaxy? How many of those have planets? How many of those planets are Earth-like? And so on and so forth. Well, we know Milky Way has about 100 billion stars. That first number is pretty large. We also know that the fraction of stars that have planets is very high. On average, it's 100%. So we're still at about 100 billion. And then as we go on and on in these terms throughout the Drake equation, especially what we know now from Kepler, TESS, and all of the ground-based surveys, Earth-like planets are extremely common, more common than we ever would have thought about, more common than Enrico Fermi, in the 50s, or Francis Drake in, what was it, the 80s? I can't remember, would have thought when they were putting together these estimates. There's a lot of ideas, given that these numbers are so high, to help address why we haven't definitively heard from any extraterrestrial civilization. One of the ideas is this concept called the Great Filter, that perhaps there is some, I'll say somewhat off the cuff, universal barrier to life. And this could be life evolving at all, going from inorganic to organic material. We're on the other side of that here on the Earth. It could be developing a nucleus. It could be life becoming multicellular. It could be life surviving a mass level extinction event, whether or not induced by life, such as a nuclear catastrophe, or cosmic in origin, such as a massive asteroid impact. I think that's probably what I buy into the most, is that we're either on the good side or the dangerous side of a great filter, rather than there being some sort of hyper-intelligent galaxy-spanning civilization that's kept quiet. I do in my free time enjoy reading science fiction that goes more into that, but I think it's probably a somewhat more mundane explanation. Okay, we have Christian Wade asks, how would looking for exoplanets affect looking for extraterrestrial life? Great question. Those two exploration avenues dovetail quite nicely. When Michel Mayor and Didier Queloz found 51 Peg B, they were conducting a radio velocity survey of nearby stars. They weren't setting out to discover the first exoplanet around a solar type star necessarily. They weren't thinking about life necessarily. They weren't expecting that Earth-like planets in the habitable zone would be so common necessarily. And yet, 25 years later, the field has really, really exploded. And we find ourselves with a whole bunch of tools in our exoplanet astronomer toolkit to help characterize these exoplanets. So that's why I keep talking about detection and characterization, especially over the past 5 years, really with the advent of the Kepler mission. We've gone from what I refer to as stamp collecting, oh, there's an exoplanet. Oh, there's an exoplanet. It has this mass, it has this radius, it has this orbital period, it's orbiting this kind of a star, to much, much more. We can characterize the atmospheres of the planets, measure their densities, understand the formation and evolution mechanisms, including migration of these planets, and actually try to determine what it really, really means to be in the habitable zone. If you ask 100 astronomers, you'll get 200 different answers. And so one of the hot topics that's coming up right now, there's really two big future, I'll say three, I'll say four big avenues that are the future of exoplanets. One of them is extreme precision radial velocity. So trying to push the signal with the Doppler technique that you're able to measure radial velocity down to what the signal of Earth around the sun is. And so that's centimeters per second. And technologically, we're close, but we're not quite there yet. Two, I'll say is a microlensing survey. And that's exactly what Roman is going to do to complement Kepler and really give us that Mercury, closer than Mercury to out beyond Jupiter, complete census of statistical exoplanet frequency. And then 3 and 4 relate to this extraterrestrial life. So direct imaging and atmosphere characterization. And so now not only are we able to look and detect molecules in the atmospheres of gas giant planets, but we've gotten to the point where we're starting to think about biomarkers. And not only just think about them, but differentiate biomarkers that are molecules that could be produced by organic or inorganic processes. And so that would be harder to use as a conclusive proof. And biomarkers that, as far as we understand it, chemically speaking, are produced only via biotic processes or organic mechanisms. And we're there, so searches such as SETI are looking at it on one axis. They're taking these long wavelength measurements and trying to find signals that are periodic, or that have digits of pi repeated, and that kind of stuff. But exoplanet science is coming at it from another angle now and looking at biomarkers in the atmospheres of planets. All right, I'll do, we've got a couple more. So Joe Alberti, sorry if I'm butchering that. How does the transit method deal with, i.e. dismiss, sunspots on host stars? That is a great question. So there is all kinds of stellar noise. And anybody who studies stars would hate that I just called it noise. One person's noise is another person's signal. For us, as exoplanet astronomers, star spots are noise. I mean, they're not the only source of noise. You get flares, you get X-ray activity, and you get star spots, and you get a whole host of things that cause the brightness as measured from a host star, from a given star, as a function of time to vary, but that are not planet transit signals. So people do a bunch of different types of analyses. So for star spots, you're able to do Fourier decomposition and actually look at different signals and cross-correlate them with what the rotation period of the star is. So exoplanet astronomers in the transit field are immediately dubious of two types of signals. One is if you measure an orbital period that's very close to 1 day, because that's probably telling you that your sampling rate, if you're using a ground-based telescope in particular, is giving you a spurious signal. And the second is any signal that has an orbital period that's very close to the rotational period of the star, because that's probably telling you that you're measuring star spots. Even though star spots come and go, they might last tens of days or hundreds of days, any given star spot, even accounting for differential rotation, which stellar models can do, is roughly going to orbit, or is roughly going to cause the brightness of the star to modulate on its rotational period. And so that's how you kind of mentally identify and be skeptical of certain signals. And then you can, once you identify those in the Fourier decomposition, you can actually almost literally subtract out that signal. Because you'll see a bunch of peaks in what's called a power spectrum. So at different periods, you'll see signals with different strength. And if you see something at the rotation period, you can then go back and fold your light curve on that period and remove that signal. And that's one way to dismiss, as you say, star spawns. So David McCallie says, is it possible to have Earth-like temperatures on one of the super fast orbiting planets? And he notes close to a dimmer star. So yes, absolutely. And specifically because of your parenthetical aside. So in general, we know, given a star of a given spectral type, if you were to just measure the temperature at different distances from that star, we know what that temperature would be. And we know that for earlier spectral types, that they have hotter temperatures. And so you would need to go farther out in order to get liquid water. Whereas if you have a cooler star, so a later spectral type, thinking M, mid to late M dwarfs, you would need to get closer to the host star in order to have liquid water. And so that's part of the reason that for that TRAPPIST system, which has 7 planets again, and their orbital periods are in between 1.5 and I think 16 days. So all of those are several times closer to the TRAPPIST-1 star than Mercury. But you'll remember that when I showed the habitable zone, the green annular band, 3 planets fell in that band. And that's exactly because the TRAPPIST-1 host star is so much cooler that even though those planets have orbital periods of just days, several of them are actually potentially within that host star's habitable zone. These are great questions. I just got to say, everybody's really impressing. You're asking questions, some of which I don't really know the answer to. And so I'm giving kind of the astronomer's best answer, and some of which are just the cutting edge of science right now. So the final question, William Garley, is there a correlation between HR class of star, age, composition, and composition of planet, rock, gas? So this is a good question, and I'll say it's complicated. That's the very short answer. The long answer is that we know that there are a bunch of different kind of planet characteristics that we're able to measure, and we know that those are all separately functions of different properties of the host star. We know things such as, and this is what theorists have been saying for years, and it's backed up by the data that we observers have collected, that if you have a larger star, a more massive star, that the protoplanetary disk will be correspondingly more massive, and that correspondingly again means that you'll have more material out of which to build planets, and so you would expect that you would have, or at least be able to have, more massive planets, or planets with a higher fraction of solid material, so cores that are more massive and larger. And we also know that the metallicity of a star, so astronomers, the astronomer periodic table has 3 elements. It's got hydrogen, it's got helium, and it's got everything else. And we call everything else metals, much to the chagrin of every chemist, going back to Mendeleev. So here, metal means lithium all the way up to ununnium and beyond. So stars that have a higher metallicity in their atmosphere, we have seen, multiple groups have seen a correlation with stars with a higher metallicity have planets that are more metal rich and more dense as well. And so there's a bunch of these kinds of trends that we have measured and noticed. And we're really just kind of at the tip of the iceberg. So thank you, everyone. It looks like those are all the questions I see here. Thanks for the great questions. Thanks for letting me play around with the poll. I hope that was fun. And thanks again for giving me the opportunity to talk. It's great to see a bunch of familiar faces, Carol and Jackie and David. Next time, hopefully I'll be able to be there in person.
Great. Calen, we did get one question from Facebook, and unfortunately, I cannot pronounce this person's name, but this is the last question. It says, how easy is it to detect moons orbiting around exoplanets?
Ooh, that's a great question. The answer is it's not very easy at all. but that doesn't mean it hasn't been done. So a friend and colleague of mine, his name is Alex Tichy. He did his grad school at, I think it was MIT, with Professor David Kipping. David Kipping has been looking in Kepler data to find what we call exomoons for years. And so as you would imagine, the moons are going to be very difficult to detect because they will, in general, be much smaller than planets will be. And you need just an incredible set of extra factors to kind of go your way. You know, their period, their inclination, et cetera, et cetera. So there has been, oh gosh, if I'm remembering the name right, I think it's Kepler 1652, 1625, maybe 1625. Kepler 1625, which is known to host a planet, they have published a result that has said that there is indeed an exomoon signal, or at the very least, a signal that is congruent with being from an exomoon. Now, excuse me, it's very difficult to follow these up, and we don't really have an experiment, space-based or ground-based, that is designed specifically to detect exomoons. I will note that the Roman Galactic Exoplanet Survey, specifically the microlensing component, it won't be quite so easy with the transit, but it'll still be possible, will in principle be sensitive to exomoons as well. But the expectation for the detection rate is very, very low, less than 1. That's a great question though. You know, in early 90s, who would have thought that in 2020 we would be talking about putative, if not probable, detections of exomoons, not to mention exoplanet.
Okay, sorry, I butted in on the picture here. I think that's all the questions we've got. Obviously, I'm very happy my son was able to make this presentation, and that he didn't waste all of his college years drinking beer like I did. So
not all of those years.
Okay, well, okay, I think everybody's watching. We should probably be quiet on this. So anyway, Calen, thank you very much for coming and doing the presentation. I wish you were here, but this is the next best thing. Everybody else, thank you very much for attending. We had a lot of good questions, and Calen, you probably couldn't see them. You got many, many comments about how they enjoyed the presentation, and you know, it went over really well.
And I should say that I'm happy. I'll send a PowerPoint version of my slides to this ASKC president. And so if there's a listserv or something and people would want to access it, I'll be more than happy to share that. So thanks again, everybody.
All right.
Until next time. Ad astra per aspera. It's times like these that I'm reminded of the Kansas
We've got a
State.
little bit of club business and announcements to go through. Okay. I'm going to ask Melinda to give us an update on the library.
I just wanted to say that I have put in a book order. We're going to have 22 new items in the library, otherwise known as the house for the time being, since they're not going to physically be in the library, but much easier to check them out that way. So they will be posted in the Cosmic Messenger. Some of them were pre-ordered, so they will not all be available at the beginning of August. Some of them will be available later, but we're gonna, I'll be adding those to the library, and then you can look at them on there, and you can, in LibBib, I mean, and you can put them on hold from there. So you can put them on hold from there. You'll be able to see that they're actually in at that and added to the library, and you'll know you can get them. And to get them, I can drop them off, deliver them. You can meet me somewhere, whatever, until we are in person again, like normal. So, but yeah, 22 items. I'm really looking forward to it. I had a great time picking them out, and I thank you all for the suggestions I got.
Okay, thank you, Melinda. By the way, we just had a question come up, and I'm going to pass this on to Carol Org. I had a question about the AstroLeague, AstroLeague election results. So I've just requested that, Carol, if you could start. There you are.
Okay, greetings everybody. As far as the answer to that question, yes, we do have results, and I was dumb enough to accept another 2-year term as president of the Astronomical League. The other contest that was up for election this time was the vice president, and that will be filled by Chuck Allen. And so that's the two that were up for election this year. All right, I won't bore you with details about the 4.5-hour Zoom meeting we had, our national meeting, which we can press from 8 hours down to 4.5 hours on a Zoom meeting. Fun as far as replaying that. But anyway, here is some things of interest to lots of our observers in the club. We have 5 new award programs that were announced at that meeting. The first one is Foundations of Imaging Observing. The second one is a Master Imaging Award. And the third one, and this is going to be lots of fun, it's called the Alternative Constellations Observing Program. And that's deals with lots of very unique and unusual constellations that aren't very popular anymore, that nobody ever hears about, but we're reviving them. And the last one is a unique Library Telescope Award program, and there'll be much more information following about each of those. And that's about the extent of my AL meeting for right now. Thank you.
Okay. So I'm going to ask David Young to give us an update on Powell Observatory.
There we go. The board of directors has decided that Powell will be closed to the public and no programs will be scheduled for now. But Powell is open for members, and there have been some impromptu gatherings on the grounds. Powell can still be reserved by members for small groups subject to some restrictions. I've been inundated with calls about the observatory and NEOWISE. There's probably some more people out there tonight, even though we're not officially open. I figure the pandemic has cost us $30,000 to $40,000 in income since we can't host any people. The Powell staff and other members haven't been idle, and we've had numerous improvements to the observatory, to the wiring and cabling, and we're also making progress on the Astro Imaging Center. The observatory does still need some maintenance. Randy Stewart is taking care of the mowing and trimming, but the weeds are getting a little out of hand inside the dome, and frankly, I can't do all of it. If you can lend a hand, please give me a call. Remember that you can contact all of the club officers. The information is in every issue of the Cosmic Messenger, and most of us have our phone numbers listed in the club directory available on the forum. And that's all I have for now.
All right. Thank you, David. All right. Well, thank you, everybody. We're going to say goodnight here. So stay safe, stay well, and we'll see you again next month. Good night, all.